I'd like to thank the organizers for inviting me to this conference. I always enjoy it. So I'm going to switch gears here and tell you about a different type of cold Rydberg atom molecule. And that's a molecule that can be a molecule formed by two excited Rydberg atoms and bound together at very, very long ranges, say microns in length. So the bond length is up to 10 microns. And they're formed, instead of this novel binding mechanism, by more or less van der Waals forces and the avoided crossings that inevitably happen in these dense manifolds of Rydberg atom interaction potential. So, for example, here's shown a bound well. There's another one, another one, another one. And one of the novel things about these types of molecules is those wells and the shapes of those wells can be tuned with electric field. So here you have no bound states at low background electric field, 0 millivolts per centimeter. And then as you crank up the field, you get these avoided crossings where you can form molecules. And then as you increase the field, you can then kind of get rid of them as the star shifts and the avoided crossings then don't support those states anymore. So Rabban, who is going to give the next talk, coined this term, I think, macrodimers, and that's because of the enormous size of this bond, these micron-sized bond lengths. And what I'm going to tell you about is calculations of these things, and then also the experimental detection of them. And I'll tell you in kind of a storybook way, because my group does a little bit of calculations, but we mostly do experiments. So these, again, are made by multipolar interactions, mostly dipole-dipole interactions. The shapes of the wells are tunable with the background electric field. Long bond lengths, as I said, macrodimers. And then these things are, the wells are very shallow and they're very broad. So these things are almost semi-classical. There's a continuum of states. So you don't really see any resolved vibrational structure in the molecules that I'll tell you about today. Now, kind of the motivation besides trying to detect something that's kind of cool is that, and how we started out, is that all the things that we've heard about today depend on knowing what the interaction potentials are between Rydberg atoms and knowing what those interaction potentials are with a background electric field, because most of the experiments have or possess some sort of background electric field, and because of the high polarizability of the Rydberg atoms, that background electric field matters. It can change experiments. So one aspect of this work is that the macrodimers are very sensitive tests of, and their existence is a very sensitive test of the potential energy calculations that we've done. Okay? So let me tell you a little bit about the experiment. So because that's going to be kind of the primary thing that I want to discuss. We do our Rydberg excitation with cesium atoms in about the same way that everybody else does theirs. We do 2-photon process where we excite up into the 6p 3/2 for cesium, and then we use a green laser to excite whatever Rydberg level that we choose. Our experimental setup is a little bit different because we have a time of flight spectrometer built inside a vacuum chamber, and that magneto-optic trap, all the experiments that I'm going to tell you about today use a magneto-optic trap. It's built inside there, and then there's a long time of flight, and then there's a detector down here that we use to detect the ions. We've just added a dipole trap here so we can get to higher densities. We haven't done any real experiments where we have good data from that, but it's just coming online, so we should have some soon. Okay, so the way that we detect the Rydberg atoms after we excite them is the same way that almost everybody else does. We use pulse field ionization. The thing that's slightly different about our experiment is that because we have a high resolution spectrometer, what we can do is look at the time of arrival of the ions as they hit the detector, and from that we can extract what the velocity distribution of those Rydberg atoms are after they leave some sort of process. So in this case, when we look at two atom processes, we're going to look at what the recoil velocity of the two atoms is, and we're going to use that to get a kinetic energy, and that's going to tell us something about the process that we were exciting. Okay. To do spectra, of course, what we do is we just sweep the green laser. So we step the green laser in time, and then we collect the ions, and then we look at that signal. So that would be to take a spectrum. To look at these velocity distributions, what we do is we sit on a particular feature, and then we collect the arrival time distribution on that detector. Okay. So in a sense, this is a differential method in that we can detect the kinetic energy of the products after we've excited them. Okay. So if you take a spectrum of one of these Rydberg gases, of course, here it's shown not blown up, but and as a function of electric field. So this is the laser frequency. This is the electric field that's applied to the plates as the Rydberg atoms are excited. You just collect a Stark map. But for any field, if you kind of look at the baseline here of that spectra, you'll see other small features here that don't correspond to Rydberg states. Okay. So the first thing you think is that these have to be due to pairs of atoms interacting. It would be the first thing that would show up in this low-density gas. And so the question we originally asked is, can we predict the positions of these, and can we understand what they are? Because in these kind of not too steep potentials, you can actually excite on the asymptote of the potential. You could excite at any real stationary point on those potentials. So some of these things correspond to bound states. Some of them would correspond to states that would fall apart or dissociate after excitation. And so being able to predict that again is a nice test of your potential energy calculations. And so the two goals after seeing this were to, one, calculate those pair interaction potentials and see if they corresponded to these features. And then the second would be to experimentally investigate each of those features, or at least some of those features, to determine if those potential energy calculations and their shapes were accurate. Okay. So here are the two possibilities that you have. Kind of, you could say at an avoided crossing or any stationary point, as I said, you could excite there. Those atoms would then dissociate after excitation. In a sense, you could think of them as rolling off this potential curve, and as they roll off, they gain kinetic energy. So in that way, you can actually determine where this point is relative to the asymptote, and then you can test your potential energy calculations. You could also excite into a bound state, which I showed you on that first, on the introductory slide. There are bound states. That's one of the things we noticed when we were doing these calculations. And these guys are a little bit harder to detect because, as I said, they're very broad. You know, these things have wells that are, say, several microns wide and only, say, something like 40 megahertz deep. So, you know, in a square well, if you have a shallow square well and you stretch it out, then you're going to get a high density of states. And basically, we calculated the bound states in here. There were lots of them, and they were basically a continuum based on what the radiative lifetime of the Rydberg states would be. So we had to figure out a way to detect whether the features that we would predict that were bound states really were bound states. And we were going to use these velocity distributions, and I'll show you how to do that. Okay. So first, I'll just say a little bit about the calculations. I know some of you have seen this before, but just for the people who haven't, the reason why you can get these strong interactions between these Rydberg atoms is that they can undergo processes like this. So this is representative of one Rydberg atom, another Rydberg atom. This is in, say, one state N that's in the same state N. And there's cases where this guy can, say, increase in N, and then there's cases where this guy can decrease in N, either allowed by dipole transitions or quadrupole transitions. And it's the addition or the adding up of all these things that gives you the van der Waals interaction. And the way that we do our calculation is we just expand our basis state and diagonalize a big matrix to calculate those van der Waals interactions because the density of the Rydberg states is so high that there's lots of avoided crossings. And so instead of going through finding the avoided crossings and trying to do, say, degenerate perturbation theory around those avoided crossings, we just use a big computer, diagonalize the interaction, and then we get our result. And we can add an electric field to the calculation by using, say, a Stark-shifted basis state or including the Stark shift part of the Hamiltonian into the diagonalization. Either way is fine. So for the calculations I'll show you in the first part of the talk, we're going to choose the electric field to be along the internuclear axis. What that really ignores, and that's valid for all the calculations I'll show you in the first part of the talk, what that really ignores is the polarization of the atoms. So since the Rydberg atoms are highly polarizable, you'll, with the electric field, induce a dipole moment, alpha times E, and then you'll see those dipoles interact, and that will be angular dependent depending on the direction of the field relative to the internuclear axis here. So in most cases, that effect is very small, but as you increase the field and go up an n, that effect can increase. And at the end, in some of our newer calculations, I'll show you that there is this angular dependence and that it can be significant for high n state. But this is just the dipole part, and this is the coordinate system we use and how we do the calculation. So diagonalize a big matrix. What comes out is something like this, and you get lots of states. There's lots of crossings. They don't all interact, but some of them do. So it's important to understand this and understand at least the energy ordering if you're going to do an experiment, because there's really a lot of curves. And if you apply strong lasers, for example, you can AC star shift the levels around, sweep them through each other, and then you'll get results that will differ from what you expect. For example, this just shows one example of the difference between zero field and a very, would qualify as a very small background electric field. You can already see here that these potential curves change quite a lot with that small electric field. For example, this state has only a very small well here. It doesn't support any bound states, but when you apply the electric field, now you have a state that is much deeper than with zero field. And this is for 89D, so fairly high principal quantum number, but very small field too. I mean, this field here is a weird number because that was the background field that we had in our apparatus when we started doing some of these experiments. We've made it a bit better, but that was just what sat on those big electric field plates. So how do you tell the difference between a collision, say a photodissociation event, a bound state molecule, and how can you distinguish those two types of process? So the ways that we came up with were to analyze this arrival time distribution on the multi-channel plate detector in our apparatus. So this curve here, what it's showing is what is the dependence of that full width half maximum in spatial units as the particles are collected on this detector and hit. Basically, it's reproducing the arrival time distribution as a function of the delay of the pulse field ionization. So we excite Rydberg atoms or pairs of Rydberg atoms, depending on the experiment. We wait some time, and then we pulse field ionize those atoms. And what these curves represent is what the width of that arrival time distribution is as a function of that delay time. So down here, this is just if you would excite atoms. What you would see is a narrow arrival time distribution just based on what the thermal distribution is in the Mott. This is in spatial coordinates here, so then as we delay the pulse, what we would see is those Rydberg atoms expand out of the trap, and then the arrival time distribution would broaden. Okay? So this is just taking the thermal distribution, exciting atoms, watching them expand, and then we collect them on this detector to reproduce what that distribution of velocities is. And what you get out, depending on what the temperature is something that represents the Boltzmann gas of the atoms in the trap. Now, for a collision, which is represented up here, what you do is you excite those two atoms close together on those potential curves, and then as you delay the pulse, you can watch the atoms kind of fall away from each other in time. Okay? So at short time, what you do is you end up stripping both the electrons off of the two atoms. So you create two charges very close to each other, and so you see the Coulomb repulsion between the two atoms that you excited close together. As you increase the delay time, because those atoms were free to kind of fall away on that potential curve, they're further and further away, and so you see a reduction in that Coulomb repulsion. And you see that out to some minimum where the Coulomb repulsion is negligible. So as the atoms make it out to some r where it's very far away, then you start to not see the Coulomb repulsion anymore, and what you only see is the velocity of the atoms coming off the potential curve. So if you look far out here, basically the slope of that tells you how much kinetic energy the atoms acquired as they rolled off the potential. Okay? So Coulomb repulsion to some minimum where basically whatever the recoil velocity is catches up, and then you see the slope of the atoms, or slope of the potential curve, or the shape of the potential curve as the atoms fly apart. Just that velocity. In contrast, if you have a molecule, the two atoms are bound close together. I mean, the definition of a molecule is that there's a bond and that the atoms are going to stay in the same proximity. So what you would see if you excited a molecule as a function of this delay time is you would always just see the Coulomb repulsion of the two atoms as you ionize both of them with this pulsed field. So here you just see the Coulomb repulsion of the two atoms because they're stuck together. So you always see the same amount of, the same width of your arrival time distribution. Okay. This calculation here is if the atoms started out at 3 microns to one another. That's the same here. This is if they were at 7 microns. These are the two cases for the collision there. And a 20 centimeter per second velocity of the atoms as they leave some sort of repulsive curve. Okay, so this is a way we can distinguish between these different processes, and so we can test these calculated potential energy curves. Okay, so the first thing you want to do is you want to test to see if you can what you can resolve. You know, you have to have some sort of control, and so the first thing we did is we just excited Rydberg atoms in the magneto-optic trap, and then we applied different fields, different laser fields to do polarization gradient cooling to make that cloud really cold, and then we reproduced those temperatures by looking at the temperature of the Rydberg atoms that we excited. The laser absorption on the Rydberg transition, the two photons don't really impart any, don't really heat the atoms very much, and so by detecting one at a time here, this is a little bit deceiving, but it's kind of trying to show you what the idea is. So we detect one atom at a time here. You can actually show that you can get about this is what we were able to do for this experiment, get about 2.5 centimeters per second resolution in this. Okay. Since then, we've done a little bit better, but not much. A lot of the limits on our resolution now are determined by things like laser stability and the stability of our electronics in the lab, because it really depends on how well you can time the arrival of a pulse hitting that detector from an atom. So the idea is this, and so what I'll first show you is an example where we excited something that turned out to be one of these photodissociation collisions. So again, the idea is take the two atoms in the intermediate state, apply photons of known energy, and then you can determine what those two states were by measuring this kinetic energy. So it's just using conservation of energy. Okay, first we wanted to show that it was a 2-photon and 2-atom process. So again, we did some preliminary experiments just to show that the resonance was what we thought it was. And you can do a couple different things here. You can look at the signal as a function of intensity, and you can compare what you would get if you just excited Rydberg atoms to if you sat on that little resonance there. And so what we show here is that if you sit on this resonance, you get a slope of 2, which means 2 photons had to go, 2 green photons. This is a function of the green laser intensity. This just shows that 2 green photons were needed to excite that, and just 1 was needed to excite that. So that tells you that there's 2 photons that enter into the process. The other thing you can do is vary the ground state density. We did the 6p3 density, and that should be quadratic because it takes 2 6p3 atoms to make one of these diatoms. And then the third thing we did to prove this was that we looked at the charge distribution on the arrival at the detector, and just taking into account the statistics of how the detector detects the pulse. So what is the quantum efficiency of the detector? You can see that this gives a much higher 2-ion detection than sitting on this resonance here. So what this says is that when you ionize at short times here, you're really producing 2 ions versus 1 ion when you sit here. So all that gave us a lot of confidence that this peak here was really due to a 2-atom process. We did the measurement here where we measured what those velocities were, and we compared it to the temperature of the trap. And what you could see is that we got here a recoil velocity of each of the atoms of about 17 centimeters per second. Okay, so that begs the question, does this match the potential energy curves that we can calculate for this particular state? And indeed it did. So our little line here sat in this region of these potential curves just to the red of this 89D state, and it corresponded to an 88D plus a 90D. That's not really that important, but what is important is that if you looked at the state that we excited, here is the fraction of the 89D state in this particular wave function, and here's what we think is the Frank-Condon point. You can see that this actually matched pretty good. It probably matches better than what the accuracy of our potentials are. So some of this is probably just fortuitous because we think the potential energy curves are good to about, say 2 to 4 megahertz, the way that we're calculating them, the way that we looked at the convergence of the calculation. But still, very good agreement. We saw a state that was dissociative. It did have a stationary point where we could excite. So again, this is good evidence that the curves are pretty accurate. So also in the course of this work, this is the same group of curves that I showed you before. We noticed that as we changed the electric field and we shifted states through one another, we would get avoided crossings that then had potential wells here and here and here. And again, what's neat about this is that you can actually, with an external field, tune in whether you can form a molecule or not. So this is a form of control of these potential energy curves that you can use. What we wanted to do is see if we could observe these states. And again, like I said, we had calculated that they had many bound states. Just a few of them are shown here. You can see that these are the two curves shown right here, C1, C1. So this one's at 30 millivolts per centimeter. The other one's at 60. And then C2 and C2 prime, 30 and 60. And you can see that you can change the shape of the well with the electric field, and you can even change it more dramatically, as seen in the last kind of panel of the previous slide, where there aren't any more potential energy, or there aren't any more bound states. But these guys support, say, 3 to 350 bound states, and their kind of radii of lifetime broaden all those together. So really what you would see here in the spectrum is just a mush that's slightly broader than an atomic line if you're careful about your laser intensities. So that's not so convincing because you can also excite on these asymptotes. So that's why we developed this, more or less, this Coulomb repulsion, or this, time of flight spectroscopy, or what really amounts to a Coulomb explosion experiment. By some people, normal Coulomb explosion experiment, some people would be sticklers and say that you have to strip off all the electrons, but just for the sake of the mechanics, that's more or less what we're doing. So the first thing we did, aside from calculate those bound states, was to look at the lifetimes to see if it was worth to look for these kinds of states. And of course, if you do Landau-Zener on these, what we get is a very long lifetime, something on the order of 100 milliseconds, which is a lot longer than the radiative decay time. So that's what, this is really what limits the lifetime of these molecules. So the first thing we did was looked up into high-end states, but, and we did a line shape analysis, but we only saw some mush of stuff, and that wasn't very convincing to us. And since what we had to do is we had to count individual events, so this is a little bit different than a lot of the other experiments you've heard about. We're just counting, one event at a time. It was hard to find things at higher end that we could actually do a clean experiment on, because these things show up a little bit because of intensity borrowing from these 89D states. Because you're taking it's a non-resonant 2 photons, so the closer you can get to some sort of resonance, the stronger that particular peak would be. And since we don't have 2 lasers to do a resonant excitation, the 2-color experiment, we had to go down and find some states where we were far enough away from this to not get background counts, but close enough to it that we still had some oscillator strength. So close enough to the main Rydberg lines. And that happened around n equals 66, and we looked at the 66D states, which we found did have some pretty strong potential wells here. So you can see that these things are maybe 30 to 50 megahertz deep. And you can see here that from the inner turning point to maybe the outer turning point towards the asymptote is about 3 microns, and the center of the wells are somewhere, what we call the minimum of the well is somewhere around 3.5 microns for these cases. Okay. So again, to detect these, what we're going to do is we're going to sit on that upper resonance, the one that was furthest to the blue in that last slide, and what we're going to do for a variety of states near that 66D state is we're going to look at this recoil distribution, and if it's a molecule, it should sit and have basically over some delay time the same time of flight velocity distribution, or the arrival time distribution. If it was a collision, what we should see is that arrival time distribution shrink and then start to expand again. So this is just simple kind of kinetics. So here's the states we examined, because of course that kind of for similar states you're going to get similar structure from these these Rydberg atoms because of the positioning of the states energetically. We didn't do all the same experiments we did last time, but we did look to see what the intensity dependence was, and it was quadratic. So we convinced ourselves that these were all 2-photon processes. You need 2 photons to create them. And then we sat on the line and looked at the time of flight or arrival time distribution, and we compared the red, which is sitting on the molecular peak here, versus the Rydberg atoms, and you can see that this is much broader than that. If you compile that data for the 3 states, you can see that these are relatively constant, and these are what you would get for a collision which was recoiling at 2.5 centimeters per second. So this data we think is pretty convincing that these guys are bound together and stay in the same vicinity for this long time, meaning that they're a molecule. Here's some data from the atomic line for that same region, so you can see that this is always much broader than the atomic line. Just to be thorough, we measured also the same thing for that 89 D state collision, just to show that you get the Coulomb repulsion and then it kind of flattens out here. And so this is the 89 D state. It's a bit more noisy because we're closer to that atomic line, and that gives you a little bit more noise. You pick up some atom counts from the wing of that atomic line. Okay, so we think we detected these macrodimers. We think that their position and their structure agrees pretty well with our calculations. Kind of the newest thing we wanted to do was we wanted to go and examine or look at this idea that as you increase the electric field, the potential interaction between the atoms is not going to be isotropic. It will be anisotropic. So here's one of our first calculations where we show E parallel to R and then E perpendicular to R. These are for very large fields, probably too large to really look at in any sense. But you can see that there's big changes. But what I'd like to show you is the newest calculations. Really 0 to 90 is all that matters. But this is for the 90 D state. And this is at 3, 4, and 5 microns. And what we've done here is done our full calculation, and then we subtracted out the van der Waals part of the interaction, so the part that's isotropic. And what we've looked at for a field of 100 millivolts per centimeter is the part that's anisotropic, that depends on the direction of the electric field versus the internuclear axis. And you can see that these interactions are, for this field, are pretty large. And this field is chosen so that it's also, it also isn't that we're driving the D state up into the Stark manifold. So we think that this is a doable experiment to actually observe this anisotropic part of the interaction. And the other interesting thing about this is it doesn't really, well, these points here, more or less, are kind of not on this line of the kind of standard dipole-dipole interaction because there's a crossing between another curve around here, and so we get some perturbation of this. But this also doesn't scale like 1 over r cubed, because as the dipole-dipole interaction mixes the states, the polarizability is changing as well. So that's another interesting feature here. So I'd just like to conclude, electric fields matter. We observe macrodimers. And then I think an underlying thing in this work is that as people want to go and do experiments in ultra-cold chemistry where they're going to look at more than 2 atoms, say 3 atoms, you need differential techniques to be able to get a fingerprint of what's happening. If you just look at product yield, you can get fooled in kind of quantum or physical chemistry experiments. So having energy resolution, angular resolution, gives you a fingerprint of what's happening in the experiment. And here's the people that did this. Richard's working now at UVA. So thanks.
So thank you very much for this nice talk on a different kind of Rydberg molecules. Is there questions to this talk?
Presumably, in your current experiments, you have no control over the relative direction of the electric field and and the axis of the atom. So, in fact, what you observe is some average over.
Yeah, what we observe.
It's a rotational average over the whole lot.
What we observe now is we average over basically, I would say, the impact parameter. So we average over the angles of the internuclear axis. Now, what we do have, though, is we will have control over the direction of the electric field. And so what we should be able to do is get what the equivalent of like a beta parameter would be in a quantum chemistry experiment. We put some sort of directional axis in the experiment, and then if we look at the angles that the particles come out at, then we should be able to see some effect of the anisotropic interaction.
Okay, it's time for a short question. Urgent? Yeah.
Is it very difficult to measure ion-ion coincidences? Because then you could get directly straight lines for coming from one event, right?
Yeah, we would need different electronics, but it's possible. You have to be able to, the way that the detector works is it has two orthogonal delay lines, and it sends pulses down either side, and then by timing those pulses, you can see where the particle landed on the detector. As long as they don't land in the same vicinity, you can use some electronics to detect both of the pulses coming out, but you need a different TDC than we have. So, possible, yeah.
Okay, so thank you very much.